Hi, this is Kenny Lee, and let's talk a little bit more about Coulomb's law and how charges and the distance between those charges affect the force between those two charges. So, if I rub some charges off this piece of wool onto this plastic comb or wand, I'll use my train Coke can to show you about force. Come on, follow. So how does the distance between charges and the amount of charge affect the force? Let's look at Coulomb's law and use proportional reasoning to figure some things out. Okay, proportional reasoning using Coulomb's law. So Coulomb's law, static electricity, or the force between two charges, is equal to K, that constant, which is 9 times 10 to the 9th newtons meter squared over Coulomb squared, times both charges divided by the distance between the charges squared. So this is an inverse square law, similar to universal law of gravity. So how can we figure out a problem like this where we have to figure out what happens to the force between two charges if we increase or decrease the distance by 1/4. So we're actually bringing the charges closer. So what would happen to the force? So if we take a look at this, if we increase either the charges, the force should increase. If we increase the distance, the force should decrease. But in this case, we're decreasing the distance. So that means we're bringing them closer, so the force should get bigger. But by how much? That's where we use proportional reasoning. So the first thing to do is kind of set up your baseline for this. And the way I do it is I start off with the equation and ignore any constants. So I would ignore K and change everything to 1. So 1 times 1 over 1 squared gives me 1. So that's my base, is 1. Now I can see what happens if I actually change it to whatever the problem gives me for a situation. So Fe equals K Q1 Q2 over R squared. Again, ignore the K. And it says if the distance is 1/4 as much. So the charges stay the same, so I keep them as 1s. But the distance is 1/4 as much. But that's squared. So 1 times 1 is 1. 1/4 squared is 1/16. And so since that's on the bottom, we flip it up. And so the force should be 16 times greater than it started off originally. Let's look at some more examples. But remember, our baseline, if we get rid of K and change all the charges and the distance to 1, just gives us 1. So we're going to use that as a comparison point. Okay, we've got two examples here. Let's do this one on the left first. What would happen to the force between two charges if one of the charges were doubled? Okay, so start off with our basic equation. Now remember, when we got rid of K and changed everything to 1, F became 1. So we're going to, again, ignore the constant. We are going to change 1. We're going to double one of the charges, leave the other one the same, and leave the distance between them the same. So 2 times 1 is 2. 2 divided by 1 is, 2. And so the force is twice as much. So the force is doubled in strength, which makes sense. You double the charge, you should double the strength. Let's try this one. What happens to the force between two charges if one charge is doubled? Okay, so we double one of the charges like what we did over here, and the distance between the charges triples. So they get 3 times further away from each other. So Fe equals K Q1 Q2 over R squared. Again, if we ignore the K and had everything as 1s, we get 1. But in this case, we double one of the charges, leave the other one the same, and we triple the distance between them, but that's squared. So that's 2, 3 squared is 9. So the force will be 2/9 as great as it was before. Let's do a couple more examples. All right, on this one, what would happen to the force between two charges if we double both charges and reduce the distance between the charges to 1/3 its original value? Okay, so again, start off with your equation. Let that equation be your guide to thinking. Don't worry about the constant. Okay, we double both charges, so they go from 1 to 2, and 1/3 its original distance. So we bring them closer together, but that's squared. So the top, 2 times 2 is 4. The bottom, 1/3 squared is 1/9. But that's a fraction on the bottom, so we end up flipping it up. So that will become 4 times 9. So that becomes 36 times as great as it was to start off with. So not only do we increase the charge, which would increase the force, but we also reduce the distance, which would also increase the force. And between the combination of those two, the force is 36 times the amount it started off as. But what if we are just going to ask, like, how can we get a certain force? So this question asks, what can we do to the charges or the distance to reduce the force between the charges to 1/4 its original value? Okay, so we still got Fe equals K Q1 Q2 over R squared. And again, we can ignore K on this type of problem. But we want the force to be 1/4 as much. What can we do to the charges and the distance to get that? Well, we have a lot of options. One, we could double the distance. Because if we do that, let's string these out. 1/4. If we keep both charges the same and double the distance, well, that will be 1/4 as much. Or we can, let's say we can half both charges. So we can have 1/2 times 1/2 over 1 squared. That would still give us 1/4. Well, we can, one charge is 1/4 as much. And so we can have one charge 1/4 as much and leave the other charge and the distance between them the same. And we can do more stuff, more different combinations of this. We can have one charge get bigger, the other charge get smaller. There's all kinds of different combinations that we can do. But you can see there's a lot of things that we can do to get to 1/4 the charge. Probably the simplest is just simply doubling the distance. That would get us down to 1/4 the charge. But if we couldn't change the distance, we could reduce both charges by half as much. But anyway, just using these proportions, just use this equation as a guide for thinking about what they're asking you to do. Thank you. Tune in again later for some more physics. Goodbye.